In this video, we are going to continue looking at induction, but we're going to prove a version of induction called strong induction. So first, we're going to review what regular proof by induction is, just the one we learned on the last video. We're going to extend the reasoning that we used in proof by induction to strengthen the induction hypothesis. We're going to demonstrate how strong induction reasoning works on a theorem called the fundamental theorem of arithmetic, which you're actually familiar with, maybe not by that name though. And then we're going to actually prove that theorem by strong induction. All right, so just a reminder of how we prove those steps in a theorem by induction. We first prove what's called our base case, and that is the first case, which is usually n equals 1, but could be another one. In fact, the theorem we're going to prove, we're actually going to start at n equals 2. Our induction step then, we assume that the theorem is true for n equals k, where k is at least 1. And then we prove the theorem is true for n equals k plus 1. So in comes some arbitrary case that we presumably have already proved, and then we use that to prove the next case, n equals k plus 1. So again, just as a reminder, why are we allowed to assume the case n equals k when we are proving the case n equals k plus 1? Well, remember that Python function model that we used to understand induction? The function shows us how to get from the step n equals k to the step n equals k plus 1. We prove the n equals 1 case, put that into the function. That gives us the n equals 2 case. That means we just proved the n equals 2 case. We can put that back into the function, and that will give us the n equals 3 case. And then we just keep on going. The idea is that n equals k case represents the case that we just proved, and the n equals k plus 1 case is the case that we're going to prove. Then that n equals k plus 1 case becomes the one we just proved. We put that one in as our n equals k, and then we just keep on going. Right? Every case is proved by doing this, and again, that's the general idea. But when we do this, it's really important to realize that we're not using the full strength of what we know in our induction hypothesis, in our assumption that we use in induction, that n equals k case. So let's think about what happens when we're trying to, being very specific, when we're trying to prove the n equals 4 case. Well, once we get to the n equals 4 case, the last one we proved was the n equals 3 case, right? We just proved that the n equals 3 case is true. However, in proving that the n equals 3 case is true, right, that's our induction hypothesis, we actually verified that the n equals 2 case was true as well, right? Because in order to prove the n equals 3 case, we had to use the n equals 2 case. And if we're really thinking about it, when we proved that n equals 2 case, we had to use the n equals 1 case as well. So by the time we get to the n equals 4 case, we've already proved the n equals 1 case, we've already proved the n equals 2 case, and we've already proved the n equals 3 case. So the question becomes, well, if we've already proved those, why can't we use those to prove the n equals 4 case? Well, we can, because we've already proved them. So if we're proving the n equals k plus 1 case, this is the general inductive step, what we're able to assume is not just the n equals k case, which we've been doing, but we can assume any case starting at n equals 1 and going all the way through n equals k. That gives us a lot more things we're able to assume when we're proving our inductive step. So here are the steps we use in proving a theorem by strong induction. We're first going to prove the base case. That doesn't change at all. So again, that's proving the theorem for the very first case. Usually n equals 1, but it doesn't have to be. For our inductive step, we are not just going to assume that the theorem is true for n equals k, but we're going to assume the theorem is true for all cases between 1 and k. And I shouldn't say 1 and k, between the base case, which is the first case, usually n equals 1, so that's why I have it written as 1, going all the way up to k. And then we prove the theorem is true for n equals k plus 1. And again, I do want to emphasize that the lowest case you're allowed to assume is the base case, right? And in this case, I'm saying the base case is 1. That's why I have 1 there. But if the base case is 2, I would be assuming all values of n between 2 and k. All right, so here's the theorem that we are going to prove. If n is any natural number that is at least 2, so now we're starting at n equals 2, then n is either a prime number or we can write it as a product of prime numbers. In other words, it's either a prime number or it has a prime factorization. We can factor it into prime numbers. So we're going to go ahead and prove that theorem by strong induction. So let's look like we did before. Before we go to the general strong induction proof, let's see if we can look at what strong induction looks like in some particular cases. Right? We're going to start with 2 and work our way up. Well, for n equals 2, that's our first case, right? So that's our base case. And that one is just a prime number, right? So it's a prime number, so it satisfies the theorem, right? The theorem says it either has to be prime or we have to have it as a bunch of prime numbers multiplied together. Now, the interesting part comes with n equals 3, right? Because this is not the base case. However, we can't use the n equals 2 case to prove that 3 can be written either as a prime or as a bunch of prime numbers multiplied together. 2 has nothing to do with whether 3 is prime or a product of prime numbers. And in fact, n equals 3 is just a prime number independent of what we know about 2. So this is at the same time a little bit troubling because we haven't used a previous case to do the prime number, and a little bit troubling in that we can't do that. Actually, just one troubling thing. I got a little ahead of myself. Now, n equals 4 is an interesting case. Now, this is interesting for 2 reasons. First of all, it's the first one that's not a prime. And if we want to write it as a product of prime numbers, or what we think of as prime numbers, we have to break it up into 2 times 2. Now, notice that neither of those numbers, 2 or 2, is actually n equals 3. So trying to use n equals 3 to prove that n equals 4 can be written as prime numbers multiplied together is completely useless. However, if we go back to the n equals 2 case, we know by the n equals 2 case that 2 is prime, so writing 4 as 2 times 2 actually is writing it as a product of primes. We know those prime numbers 2 are prime. First of all, we kind of know them, but like if we're thinking in induction thinking, we know that because a couple steps back, we proved that n equals 2 is a prime number. Right? 2 is prime from the n equals 2 case, and that means n is a product of primes. Next, n equals 5. Well, n equals 5 doesn't depend on any of the previous cases. That's just a prime number, right? So we can't use any of the previous cases for that one. A little bit troubling because again, just like n equals 3, we can't use any of the previous ones. And so, bad news for us. We have to figure that out somehow. N equals 6, however, we can, right? So we can write that as 2 times 3. I know that 2 is a prime number from the n equals 2 case. I know that 3 is a prime number for the n equals 3 case. Therefore, that's writing n as a product of primes. All right, so that's fine. N equals 7, well, that's prime. Again, we're going to have to figure that out somehow. N equals 8. Now, this is a little bit different than any of the other ones before, because if we break that one down into 2 numbers multiplied together, we have n equals 2 times 4. Now, I know that 2 is a prime from the n equals 2 case. N equals 4 is not a prime number. However, I do know from a previous case that 4 can be written as a product of primes. So 2 is a prime number, 4 is a product of prime numbers. And so even if I don't know what that product of prime numbers is, I know I can string all those primes together to make n a product of primes. I can put that 2 as one of the primes, and then whatever the prime numbers that multiply to give us 4, I could string those together, and that gives me n being a product of primes. So now our general strategy for our inductive step is sort of becoming clear, right? So here's our general strategy. So again, what we're doing is we're assuming that all the numbers up to k are either prime or can be written as a product of primes. And we want to show that that can be done for k plus 1. And we kind of have 2 cases, right? First of all, before we do anything, we're going to check to see whether n is prime. So whether or not k plus 1 is prime. If it is prime, then we're done, right? It's a prime number, we're done. If it is not prime, then all we have to do is factor it into 2 smaller numbers. By the induction hypothesis, by what we're assuming for induction, we know that those numbers are primes or products of primes. So then we use that to prove our final result, which is that n is a product of primes. So let's see if we can put that to work. All right, so here's our theorem, here's our proof. Now, just like any unusual proof method that we use, the first thing we got to do for our reader is warn them that we're using a new proof method. So we got to tell them we're proving the result by strong induction. It's a good idea to say strong induction so that they know that, oh no, I'm not just using the previous case to prove the next case. I can use all the previous cases, any of all the previous cases to prove the next case. Now, I just want to warn you that Uncle Ted in our textbook likes to call this the second principle of induction. If you want to call it that, you can. Just make sure, whatever you do, just make sure mention what proof method that you're using. All right, so the base case for us is n equals 2 because that's where the theorem starts. We know 2 is a prime number, and so our base case is proven. So we've proven our base case. We're doing well. Now, for the inductive step, we're going to assume the theorem is true for all numbers starting at 2 and ending at k, where k is some integer that's greater than or equal to 2. And we're going to, and what we mean by that is we're assuming that every natural number n between 2 and k is either prime or can be written as a product of prime numbers. And then what we're going to show is that k plus 1 is a prime number, or that it can be written as a product of prime numbers. All right, so we've made it very clear what we're assuming and what we're trying to show. All right, so it is very clear either k plus 1 is prime or it is not prime. There is no other choice. Even if Peeves wants to be a smart aleck about it, those are the only two choices. So we're going to take each of those possibilities one at a time. Right? We're going to consider each case separately. So one of the cases is that k plus 1 is prime. If that is the case, well, we're done, right? Because if k plus 1 prime, we just have to prove that it's either prime or a product of prime numbers. If we're already assuming it's prime, one of those has already been proven. So that's not so interesting. The other case is where k plus 1 is not prime. And in that case, we can break that up, k plus 1, into a product of two smaller numbers, r and s, r times s, where r and s are natural numbers, and each of them is between 2 and k. It can't be bigger than k because that would make it so that they're not smaller numbers. And actually, neither of them can be smaller than 2 because if one of them is 1, then the other one has to be k plus 1, which is bigger than k. So they both have to be between 2 and k. By the induction hypothesis, in other words, by what we were assuming for the inductive step, r and s are either prime or they can be written as product of primes. So I'm going to write those as r is equal to p1 times p2 all the way up to pj, s is equal to q1, q2 all the way up to qk, where each of the pi's is a prime and each of the qi's is also prime. And actually, this looks like we're just assuming that they're both product of primes, but we can actually cover the case of them being a prime number. So for instance, if r is a prime number, we'll just say, hey, we're just going to say that j is equal to 1, and so we stop at p1, and r is just plain old p1. And if s happens to be a prime number, we're going to let k equal 1, which means we stop at q1. That means s is equal to q1, s is a prime number. So both of those forms of r and s work for both cases, where they're primes or whether they're product of primes. All right, so then what we have is, well, k plus 1 is equal to r times s. We can substitute the prime factorizations of r and s in for r and s. So we get p1 times p2 all the way up to pj times q1 times q2 all the way up to qk. Since each of those pi's and qi's is a prime number, that is literally showing that k plus 1 is a product of prime numbers, and that actually completes the proof. All right, so now that you've seen strong induction in action, now try to use it on the problems in the PDF file called Strong Induction that is included with this video.